All right. Okay, let's start the recording. Hey, folks. Get started. How are we doing this afternoon? I'd say about a 6.5, 7 out of 10 on average, based upon my mental statistics. Glad to see it. Glad to see a whole bunch of you. So, a few orders of business while we're getting started here. I want to talk a little bit about your projects, okay? So, in the next, I would say, handful of minutes, we will have up your first project assignment, which is giving us your groups, your group project. And we're talking about groups of 3 to 4. Again, mixed groups are fine. That's okay. One member of your group's going to have to submit who the group is, okay? And hopefully we don't have people doubling up and people are, grabbed for different groups. You can only be in one group, unless you want extra special. One group. No. Hard rule, one group. Can't do multiple. If you want to do multiple projects, do it in your own time. I know you'll all be like, but Dr. Hubicki, I want to do multiple final projects. Like, well, sorry. Okay, just one. Just one. So I want you to get that group together. I want you to pick a group by 5 p.m. on Thursday. Okay? If you have a hard, that way, the goal of that is not to have a hard grading deadline, is to make sure that everyone has a group by that point. And if you don't, we pair you up. That way you're not left on your own just because, you're shy. I'm shy. I'm not sure if Arita is shy. I am shy. I know you all believe me. Okay? So I get it, shy people. All right? So in addition, let's talk a little bit about the project in general. Let's get you some more starting requirements for your project, okay? Day 27th. So, group project update. Okay? And what I'm going to want from you, from your group, okay, you only need one submission per group. So, first off, groups due Thursday, January 29th at 5 p.m. on Canvas. It'll be a Canvas assignment, okay? And we're talking groups of 3 to 4 roughly people. I'm sorry, 3 to 5 people. I apologize. That's fine. Let's put we're going to put a little note document saying if you want it to be a smaller group, just tell us why, okay? You want it to be a smaller group. It's like, well, this is my individual graduate project, and I'm fine doing this on my own. Okay, so we'll put a little note box for any additional information, okay? So that's what we're going to do. All right, and so then a week after that, so what we want are some proposed projects. And they are due Thursday, February 5th. 29th, yeah. February 5th. At 5 p.m. Okay? And we're going to put up an assignment, and what we need you to know or have some ideas about. We want multiple ideas. Likely 3 ideas. 3 project ideas. In case one of them we don't think will fit too well with the class. All right? And what you want to describe is what task would you want in a machine learning algorithm to do? Like, oh, I wanted to predict rainfall in Alaska. I wanted to control this underwater submarine simulation. I wanted to do these things. Like, what do you want it to do? Okay? So, for each one, you want to know what the task would be. Okay? And you want to think about what paradigm of machine learning it might be. You might not have a perfect idea of it yet. You're still learning, but you've had the Paradigms of Machine Learning lecture. If not, it's on your Canvas page. It's on YouTube. You can watch it as a going to bed kind of thing. Facts. My father tuned in to one of my lectures on Thursday. He said, it was great. I really needed a nap. I was like, oh, thank you. No, he said it nicer than that. He's like, you just have a voice that puts people to sleep. I was like, well, thank you, Dad. Thank you, Dad. He meant it as a compliment. So anyway, Paradigms of Machine Learning. Like, do you think it'll be supervised? Do you think it'll be unsupervised? Do you think it'll be RL? Some other fancy thing. So RL is reinforcement, supervised, unsupervised learning. Sorry, UL. For each of these ideas, where would you get your data? Would you have access to the data that you would need? Okay? Those are the big three things that we're going to want to know from your 3 project ideas. Okay? Question. Did you do a project idea example like with the assignment or just right now for fun? For the assignment, sure. That sounds great. Because I imagine some people, it's a little too much freedom for some folks who are new to this. Okay? You ever been to one of those restaurants, like a diner that has a menu that's like a dictionary? You know, I get it. I get it. So so we'll put our heads together, give you all some examples, okay, to go off of, just as a default. Yes. They should be doing their own implementation. Correct. That is still correct. So if there are graduate students within the project that have to be different than what the undergraduate students do, the thing is, if it differs in the paradigm of machine learning, it's a little open-ended, so I can understand some of the confusion here. Odds are both of them might be supervised learning methods you're using. Maybe they're different supervised learning methods. One could be using a deep neural network of a certain kind, and some person might be using some kind of linear regression or something like that, right? So that's so if you need to elaborate in the box, by all means. They can be smaller groups. Okay, if you have a 3 to 5 of grad students, you know, just make that one of the things you might want to be careful with is like, okay, how do we do 3 to 5 different machine learning methods? One of the reasons that we're doing this now, have that talk. Yes. So meaning that, for example, let's say you have 2 supervised, you have a project you want to do supervised learning on. You want to take in data for trying to predict who's going to buy what product, you know, from a bunch of data sets. And one person might do, I'm going to do this kind of neural network. Well, and a graduate student's like, well, I'm going to do this fancier type of neural network called a recurrent neural network, okay? That's a different implementation. It's not the same piece of code. There's some critical difference in the way that you approach it, okay? If you want to get a little bit more of a preview of the different types of neural network implementations, you want to start looking at chapters 6 through 9, I think it's 9, in the Goodfellow textbook, again, linked on the Canvas page. That's where they start talking more details about these neural networks that we're just starting to get into, okay? Other questions? All right. Image classifiers. You know, you could be, you could say, hey, I want to classify, you know, this picture as a cat or a dog. Here's a cool one I saw on YouTube just yesterday. Does anyone remember there was a toy called Bop It? Could someone describe Bop It to me? Yes, hands up, yes. Yeah, basically Simon Says. It tells you what you need to do, and then you do it. It has 3 things on it. The basic version has the Bop It. It says Bop It, you bop it. You twist it, you pull it, woo, you did it. So you basically got to do it in order, and it gets faster and faster. There's a YouTuber who made a Bop It robot. I'm not saying you don't have to make the robot, okay? But, you know, as a little mechanism that pulls it, twists it, bops it, boom, you know, with a little actuator. But part of that is listening to the command. Did it say bop it, twist it, pull it, right? And my initial reaction is like, well, in this day and age, he used a neural network to determine, to classify that incoming sound signal as a bop it, twist, or pull it. Did a supervised learning method. Turns out he did something much simpler. He used something called a fast Fourier transform. Anyone here encounter a Fourier transform in there? I see some confused looks. Some people have. It's part of, I think, more of the electrical engineering curriculum. That's a linear algebra approach, right? But you can still train it on data. That's still machine learning. So you could do 2 implementations of the, did it say bop it, twist it, or pull it? Okay. One with a neural network, not one without, as an example. Okay. Again, you don't have to build a robot, but I would be thrilled. Okay. I also have a little bonus rule that I like to say. It's like, okay, that I encourage people to be ambitious with their projects within reason. Okay. So meaning that if you actually manage to try to implement something very sophisticated, something really out like that's very challenging, you do it for your research or just for fun, I like to say that ambitious projects will be great into ambitiously, within reason. Like if you show like, hey, I made this generative neural network, this thing, and it did this whole crazy thing. And it's not perfect, but look what it did. Like, hey, you know, that's interesting. That's great. And that can give you a little extra points where you otherwise would have lost some on some other part of the project. Okay. Within reason, I say, because you can't just be like, I'm going to build ChatGPT, and you sit at home and you write hello world, and you're like, I got close. You know, I'm like, come on. Ambition isn't everything. But I am encouraging you in the context of a class to try something that might be a little bit riskier if you need to. I will still probably advise you to start simple before you go complicated. You rarely start complicated. That rarely works out for you. Okay? So ambitious projects graded ambitiously is the phrase that I use. Other questions about the project? Okay. So get your groups together, submit it by Thursday. Then a week after that, we're getting your project ideas submitted via Canvas. Okay? I'm assuming everyone saw the quiz that was up, that was due yesterday. Okay? The basically, are you paying attention to the class kind of quiz. All right? We'll get up our next quiz soon on more concepts, as well as the homework. I'm still trying to get the homework working just the way I want, so it works for all of you. Thank you for your patience on that. I know you all want homework desperately. I'll get it to you. Okay? Don't worry. All right. With that, I want to continue where we left off from at the end of our last in-person lecture, okay? Because we had done a bunch of stuff coding on Thursday. We coded up these linear regressions. I thought that was fun, where we had a little line and gradient descent made the line fit the data. Does anyone remember this? Good, I see some nods. My dad doesn't apparently, but I'm sure you all do. I'm really throwing my dad under the bus. He's a wonderful person. Hope we're not listening today, Dad. Okay. All right. So so we did all of these regressions, right? Where we were trying to fit. So that was the last coding lecture. And by the way, if for more than 2 seconds I am off the screen over there, just let me know, okay? I'll do my best to try to make sure we're zoomed out. There's a slight zoom on my screen versus that, so I want to make sure you can see everything. Last coding lecture, we coded gradient descent for regressions. So we had a bunch of data, some x, some y, that we randomly made. We did a literal linear regression that is a line. You know, our y equals mx plus b, y equals mx plus b. I'm going to put the m and the b in a different color because our decisions that we made in our decision vector were m and b. Okay? And we used gradient descent to sort of give us that line. And we also did the intercept too, right? We used gradient descent to come up with these 2 quantities here. All right? And I want to take us in 2 different directions today. One is where I show you that by the proper taking of derivatives in the right context, you don't even have to do gradient descent to come up with the best answer. Okay? You don't have to iterate, guess, try again, guess, try again, step, 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 step. You don't have to choose that step size for gradient descent. You don't have to choose it. It just gives you an answer for what we'll call linear models. Okay? And when I say linear models, it doesn't mean just a literal line. It means a model that is a linear combination of terms, okay? So, and then number two, I want to say, hey, you can't get rid of gradient descent for everything. It would be nice, because then you don't have to iterate. You don't have to guess a step size and all that stuff, right? You still need gradient descent, especially for more complicated models. But where those models get complicated, particularly for us, is getting that gradient, getting that derivative, okay? So we're going to talk about a very fancy method, an important method that was invented just barely within my lifetime, called backpropagation. That's a way to get the derivative of a really complicated model that's way more complicated than a literal line or even a polynomial, okay? And we talked about that a little bit at the end of the lecture 1 week ago, where we had the makings of our first neural network, okay? So we'll go into more details about that. Okay, but first, if we're going to, so let's go back to the version where we don't have to do gradient descent, where you can just solve for the answer. So let's talk about linear models, okay? The idea, Gesundheit, is that is a linear model is one where you can make a prediction using only linear combinations of decision variables. Meaning, you have your decision vector W, okay, got all its decisions to decide inside W1, W2, up to some Wn. If you are somewhat new to linear algebra or just more mathematical notations of these things, you could write this in a much fancier way where we would say W bar, our vector, is in a value of real numbers to the n. So all these things are real numbers, to be a little bit more specific. Or a real valued vector, where this says, oh, there's n elements that are real numbers, and not just integers, not complex numbers, real numbers. Okay? Just a little bit of math background. So if we have the decision vector W, okay, so some prediction where this prediction, it will say, is just a single scalar number. Say that's a scalar value. Okay. Scalar value is going to be equal to W transpose times some input x bar. Some input vector. Okay. Now, this looks a little bit like linear algebra. Again, not a required course for this course. Okay. But this here, that little t, what does it stand for? Transpose. Standard transpose. So we're going to do a little tiny bit of review of linear algebra to describe what we're talking about, because this will be useful for beyond question. Thank you. Appreciate that. Thank you. Thank you, producer. All right. All right. Now let's go a little to the right here. Yeah. Tell you what, we're going to fix this structurally, my friend. There we go. Power of OBS here. Okay, we can see that a little better, right? And oh yeah, much better. Okay. All right. The transpose. Basically, it swaps rows and columns. So by default, as we know, like W is a column vector. So W transpose becomes a row vector. So it's going to be a row, W1, W2, up through Wn. These are not multiplied. They are spaced out in a row vector, okay, like an array, okay? And if it's then multiplied by this vector x, okay, what you get is y hat is equal to W1, W2, up through Wn. And you have some input, x1, x2, up through xn. Okay? Now, just as a review, the way that you multiply vectors and matrices, you don't just say, oh, I'm just going to multiply every element by every other element, okay? No, it's a matrix multiplication, and there's a general rule that so in this case, this matrix is a 1 by n, meaning it's got 1 row and n columns, and this one has n columns and 1 row. You can only multiply them if these two inner matrix dimensions are the same. If they are the same, you're good. If not, what are you doing? What are we doing here? Okay? And the result of that matrix multiplication is these sizes. It's this 1 and this 1. So the result of this matrix multiplication will be a 1, 1 matrix, or a scalar, just a number, right? So if you do the matrix multiplication, it's going to be this value times this value plus this value times this value plus this value times this value, all the way to the end, all of them, right? Question? Yes. This is literally the dot product. They have a fancier name for it in linear algebra if you want to sound cool. The inner product. Ooh, yeah. He's impressed. That makes one of us. Okay, all right. All right. It's a dot product. We call this the inner product. It looks like the dot products from Calc 3, whenever, or multivariable calculus when you learn that. Not too bad, right? So it's going to be W1 x1 plus W2 times x2 plus dot 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 plus Wn xn. So this is just a really simple shorthand, my friends. Right up there. Really simple shorthand for writing this, right? Isn't that nice? Okay. In general, if you want to do matrix multiplication, if you want the general matrix multiplication formula, and this is important because we will be doing a fair number of matrix multiplications as things move forward. Even though the models themselves will not be linear, we will be using linear algebra to help compute derivatives really well, okay? So general form, that if you want to say that C is equal to A times B, you say that C I comma j is equal to the sum across all k, and we'll say what those mean in just a second, of A I k times B k j, where A is an I by k matrix. Sorry, is not I by k. It's I by some value. We'll say sorry. N by p. We'll say that B is some p by m. Okay, so it'll be across all p Okay, that's the formula if you like formulas instead of just using my right-hand rule, where you take all these things, I'm going to lower that down, excuse me. For my own sake, okay. This is training for reality television. Anyway, boom. Take all these values, 1, 2, 3, 4, assuming you have enough fingers. You align them up here, 1, 2, 3, 4. You multiply finger to finger, and then add them together. Okay. Okay, so we can do matrix multiplication, that's great. We also know that the transpose swaps rows and columns, okay? But there's another cool rule that you want to know about the transpose. Okay, so let's say you have some matrix A. You want to take the transpose of it. You want to take the transpose of that, it equals A. You flip the rows and columns twice, you're back to where you started. But further, let's say you have A times B transpose. You can distribute that transpose so long as you flip the order. Okay? Equal to B transpose A transpose. Little rules here to live by, because you can't just arbitrarily swap the order of matrix multiplications, okay? Unless you know what you're doing, unless you're following a very particular property, you can't do it. Just generally, you can't do it, okay? So you have rules like that flip the order of multiplications. They do not commute. Matrix multiplication is not commutative. You cannot take one value and commute it all the way over here and expect it to be the same. Okay. So that's for the transpose, and of course we have the inverse, matrix inverse, where A inverse times A is equal to I, where that's the identity matrix. You've probably seen the identity matrix even if you've never taken a linear algebra class. You just get that in high school, high school and middle school math sometimes. The identity matrix, as you know, has ones down the diagonal, and it's square, and everything else is zeros. And it can be arbitrarily large, but it's square, meaning it's the same number of rows and columns. And you can only take this matrix multiplication, matrix inverse, if it's invertible. Not all matrices are invertible. Just like you can't divide by 0, you can't do 1 over 0, you can't do 1 over every matrix A, okay? So only if it's square and the determinant of A is not equal to 0. Don't have much time for determinants here today. You can just plug it into a calculator or like a MATLAB or a Python's linear algebra package. You can check the determinant of a matrix to see if it's 0. If you can, if it's not equal to 0, you can invert it. Okay? There's an entire math and art form. You can dedicate your life to linear algebra. This is survival linear algebra. Okay? For what we need today. All right? Those are just general linear algebra rules to follow. Can you arbitrarily swap the order of multiplications? No, you can't. All right? If you're adding matrices together, they better be the same size. Okay, another rule. All right, how do we use this? Well, let's assume for a moment that we have, let's say we want to do a polynomial regression. So let's do an example of a polynomial regression. Where we have some prediction, y is going to be some constant. We'll call it W. Call it W0 because it's, why not? Plus W1 times x plus W2 x squared plus dot 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 W n minus 1, sorry, Wn, sorry, x to the n. I'll move that to the center a little better. Now, that is not a line for almost all values of coefficients, but you can still use linear regression to solve it. Why? Because here are all our decision variables, W1, W2, W0, Wn. It's a linear combination of all these things. They're just multiplied by these x's. Okay? Which we can square or cube or quartile before, or quinticate beforehand, before we ever have to optimize. So we want to find W W0, W1, up through Wn. That minimizes our mean squared error. To a data set. Okay? Okay. Call it X train, capital X train in parentheses. Okay? And our so that mean squared error, MSE, going to equal to 1 over m times the sum, or iterate over all I, of y hat train, which is our prediction, minus our actual training data, where there are m number of data points. And I forgot a little square. Wah. Okay. Right. So it's a sum of a whole bunch of different terms. You have m number of data points. Okay. Now, this idea of summing a whole bunch of things squared, there's a way to write that in a convenient way. Imagine you wanted to square a whole bunch of terms and add them all together. Okay? Well, it's not too different from what we did here. Okay? Let's say you wanted to have w, instead of wanting to say w times x, and you have all of these terms multiplied by each other and added, you could say w transpose w. And that would be w1 squared plus w2 squared plus w1, and all the way up through the pattern, right? Okay. So, as an aside, pick this in blue. An aside. So w transpose w is going to equal to w0 squared plus w1 squared plus plus wn squared. Little aside in a different color. Looking good, Nick? Yeah, no drop frames. Great. All right. So we can do that. By the way, the idea of taking one term squared plus another term squared plus another term squared, does that look like a formula you learned in geometry at all? At all? Anything? What's that? Anyone? Pythagorean theorem, right? X squared, a squared plus b squared equals c squared? Yes, that's very much right. Or that if I have a vector that looks like this, it has a length w1, w2, all right? The distance between them is If this is W1 squared, this is W2 squared, this is W1 squared plus W2 squared, right? It's that distance. Okay. There's a general word for distance, more or less, in linear algebra. Anyone know what it's called? Rhymes with schmorm. Norm. Okay. Norm, right? So the idea of a norm, a typical distance here, if you have some W1, this here is W2, that distance there, is going to be the square root of W1 squared plus W2 squared, right? That's that distance. This is called a 2 norm. Okay? It's not the only kind of norm. Anyone want to guess why it's called a 2 norm? Well, close. You're so close. It's because it's got 2's in it. You could have more than 2 terms. You could have a third term. You could have a W3 that comes out of the board and still do this formula, right? If you ever had to do the distance formula, the Euclidean distance formula, the square root of x squared plus y squared, you could also do plus the z squared. That gives you the third dimension. If you were able to traverse 4-dimensional space, you could add another one and do a 4th dimension. That's the beauty of linear algebra, is you can transcend dimensions with just more terms in your math, right? You seem very, whoa, indeed. And aside, it's very tempting, at least it was for me. I'll speak for me, not for all of you. It's very tempting in so many sort of mathematical problems to try to intuit out geometrically how to solve problems. But that breaks down at 3 dimensions for me. Okay? But to linear algebra, dimensions are just another element in your vector. A 1,000-dimensional space is just 1,000 numbers in a list. You do a 1,000-dimensional norm. Okay? But it's called a 2 norm in particularly because it's got the squareds and the square root. So, for instance, a norm of some vector, we'll call it v, that's a 2 norm. So it's the square root of v1 squared plus v2 squared, all the way up to however many v's you got, right? That's a 2 norm. Something called a p norm. And instead of having the number 2, just have some variable p. Make it whatever you want. And that's equal to the absolute value of v1 to the pth power plus v2 to the pth power plus dot, 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 dot. I'm going to make a little more room. Thank you for your patience. Boom. Plus absolute value of, we'll do the dot, dot, dots. Dot, dot, dot. Vn, the pth power, all to the 1 over p. Because as we all know, the square root here is just 1 over 2 power, right? Okay. So this p does cool stuff, right? If I wanted to do the 2 norm, right here, this is the 2 norm, is that distance. It's the Euclidean distance, the squares, right? There's also something called the 1 norm. What does the 1 norm do? Well, it changes p to 1 and says that the distance to get from here to there is actually going to be the first vector, that, plus the second vector, that, in terms of distance. So it's actually going whoop, whoop. Anyone been to Manhattan in New York? How do you navigate streets in Manhattan, New York? Do you cut through buildings? Well, you try. I can't. Can't go diagonally through a building. What do you have to do? You can't go cut through. You have to go around, up 5th Street, up through whatever street, right? The distance you have to walk is the 1 norm. So you might hear it called, in the actual literature, the Manhattan distance. Okay? So it's a different kind of distance metric, right? So, and you can also do the infinity norm. The infinity norm If you make P bigger and bigger and bigger and bigger, what it becomes is a maximum. It becomes the maximum of what is the biggest of these things. Okay? So the 1 norm is going to be the longer distance because you go burp, burp, burp. Okay. The 2 norm, straight shot. You can do a 4 norm, you can do a whatever norm. Norm all you want all day. Okay. The infinity norm will be just, oh, there. Whatever is the maximum of this and that. And you can apply it to as many different elements as you want. Now, why did I tell you all this? One, it's fun. I wanted to tell you about what norms are, but also because you will frequently see in your textbook and similar textbooks, right, that if you want to talk about the mean squared error here, you are one way to write out, I want this term plus this term plus this term squared, is you can take the 2 norm and square it. Right? If I squared this, I get v1 squared plus v2 squared plus all that, right? Without the square root. So one way that people write the MSE up there is they will rewrite it MSE is equal to 1 over m, and I'm going to say y hat. I'm getting rid of the train and the little train stuff. It's the 2 norm of the difference between those vectors, and then when I do, I square it. If you see that in your textbook, that's what that is. That's the distance formula squared. Just an easy way to say this squared plus this squared plus this squared. We have so many cool ways to say this squared plus this squared plus this squared. We're having fun. Great. All right. So that's what the mean squared error is. This is what we called our cost function, right? It's the thing we want to minimize. How do we know that we have at least hit a local minimum? Or what needs to necessarily be true to know that we've hit a local minimum of this continuous function? Yes, question. The derivative, the first derivative is 0. That's right. We call that the first order necessary conditions because it's necessary and it's first order derivatives. We can name things in math. Isn't that nice? Okay? So we need the first order derivative of the MSE to be 0 with respect to all decision variables. Okay? We have a convenient way of writing that other than just the partial derivative, okay? We would say the gradient, right? Gradient descent. The gradient of our cost function, MSE. And sometimes to make it clear what you're taking the gradient with respect to, if it's a vector, put it as a little subscript next to your upside down triangle. That's the gradient of your mean squared error with respect to your mean squared error must equal what, friends? 0. Okay. That means that the partial derivative of the MSE with respect to W, what we call W0 up here. For some reason I started at W0. I'm going to shift to W1 or not. Yeah, W0. All the way up to, I just wanted the coefficients to have the same numbers. Okay. W n. And by equal to 0, it means that all those elements of that vector, 0, 0, equal to 0. The 0 vector. Vector. Okay. Doing all right. Cool. So, if only we could solve that question. So the gradient is a row vector, is a column vector, and you just want to make sure the zero vector is the same size, all the elements. Mathematicians, turn your ears off for the moment. It's not going to matter if it's a row or a column vector in this case. Mathematicians, earmuffs off. Okay, all right. There's a subtlety that technically, I mean, we know that the gradient is the derivative of some scalar value with respect to a vector. So you could write it, and as we have in this class, this returns a scalar value, a single mean of the squares of the error with respect to W. Technically, that gives you a row vector. So if you want to make it technically equivalent to a gradient, you say it's transposed. The gradient's a column vector. That subtlety will almost never matter, but it bothers me, and it probably is going to bother some mathematicians, mathematically inclined folks, okay? But the point is, derivative of each of those, of the mean squared error with respect to each of those elements has to be equal to what, friends? 0, exactly. Also zilch, yes. Okay, 0. All right, so if only we had a way to take the derivative of it with respect to W and set it equal to 0. Oh my goodness, friends, we absolutely can, okay? Now, it won't be the most elegant proof. I won't go through every step perfectly because I think some of the derivatives of these terms can be a little tricky to explain, but this is in chapter 5 of your Goodfellow textbook, okay, on page 107. Page 107. Okay. So the idea is that you need the mean squared error, the derivative of 1 over m of y hat minus y squared, norm, equal to 0. Now this is where you have a nice little step here, that this prediction, we want it to be a linear operation. We want it to be a matrix operation, okay? That if we have some matrix which has for every data point, let's just say the number 1 for all those columns, okay? Then your data point, x, for all these columns. Then x squared for all these columns, all the way up to xn. Okay? This would be a number where each row is a data point. Okay? Then my prediction for any particular data point is going to be equal to, call it y hat, that's the prediction, is going to be equal to x times w. Transpose, yeah, that's it. W are all of our decisions, they're all the coefficients of that polynomial. I'm going to lower this so I don't have to stretch so far. So imagine here we have our decision variables, W0, 1, 2, 3, up to n, right? Then my prediction for data point number 1 at the top here, let's say it's x is equal to, I don't know, 0.5 or whatever. Pick your data point x value, right? My prediction that all of my coefficients W will predict will be W0 times 1 plus W1 times x plus W2 times x squared, all the way up to Wn times x to the n. So in that first row, the result of that matrix multiplication is going to be my prediction of that polynomial, given my particular w's, right? And then the rules of matrix multiplication, the way it will work out is that, let's say we have how many data points? We have m data points, right? And we have, technically there are going to be n plus 1 columns because I decided to start with x0 going up to n. So starting at 0 means an extra 1 in there. Following that, okay? Go back to this, right? And then if we were multiplying by a vector x0, x1, up through xn, this matrix math works out, right? Because the size of this matrix here is going to be n plus 1 by 1. So it's going to be multiplying a m by n plus 1 times an n plus 1 by 1. So these numbers, they line up, right? The matrix multiplication works. What comes out? M by 1. A prediction for every data point. Beautiful. Okay? So that's our prediction written really elegantly. I say eloquently. Okay? So that means I can write my cost function, or the gradient of my cost function. I want the gradient, and I'll make it specific with respect to w. Make it extra clear. At the top, I put a w there as well. Of 1 over m, you see that up there? That's a constant. Can I pull that out of my derivatives? Yes, 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 yes. We can. Put it on the outside. 1 over m times the norm, the 2 norm of x w minus y, and it's the 2 norm, hence the 2 in the bottom, and we square it. It has to equal to 0. Okay? Now we knew another way to write a whole bunch of terms all squared and added to each other, right? The transpose times itself. We covered that a little bit up above, right there. Where? Somewhere. Somewhere we did. Trust me. Okay. We did it somewhere. Excuse me. So we could rewrite this as 1 over m times the gradient with respect to w of the transpose of the vector, because this is a vector, because that's a vector, that's a vector. So the transpose of it is going to be x w minus y transpose times x w minus y is equal to 0. And what are we trying to solve for here? We have an equation. We want to know the decisions. We want to know what decision to make. What w gives me a gradient of 0 and is therefore a necessary condition to being the best choice. Okay? Okay. Now, you see these terms here. You have two sum terms multiplied by each other. Then remember FOIL, first, outer, inner, last. You could apply that in a linear algebra context. I'm running out of time here today, so I'm going to push a little faster. I apologize, okay? How much time do we have? I recommend going to page 107 to follow maybe the 2 or 3 more steps. What you end up doing is you end up foiling this, then taking the derivative, and it leaves this term. Sorry, friends, I want to make sure I talk a little bit about backpropagation today. So 2x transpose x times w minus 2x transpose times y equals 0. And again, the textbook, it's the Goodfellow textbook. It's free and open to anyone on page 107. Okay? So can I solve for w? Yes. I can move this to the other side. Whoop. then all this stuff in front of W I can get rid of. I'll also point out these 2's, they'll cancel. Look at that. Shoot, shoot. They're just constants. Divide both sides by 2. We're chill, as mathematicians will tell you. Okay? So if I put that on the other side, I'm going to say that X transpose XW is equal to positive X transpose Y. And if I want to move this stuff on the front, I need to do a very simple linear algebra trick. I multiply both sides on the left, because it matters what side you multiply things on, as we know from matrices. We want the inverse of X transpose X times W times X transpose Y. This matrix is the inverse of this matrix. Assuming that it's invertible, we'll assume that it is. This becomes the identity matrix. Oh, I forgot to do the other side. Oh, my goodness. Mathematicians, avert your eyes. Okay. X transpose X to the minus 1. So this will all cancel, leaving only W. W is equal to X, the quantity, X transpose X to the minus 1, X transpose Y. No gradient descent required. There's just a couple of steps of calculus that are in the middle that I had to skip through because we don't have a lot of time left. Okay? I know there are probably some questions about that, and I apologize for that. But look how simple that equation is. Multiply some matrices, take an inverse, take a transpose, multiply by y, done. You wonder why Excel is so good at doing power 6 regressions. You can just apply that formula. You can apply that formula. You will apply that formula in Python. Okay? But not everything is a linear combination of decision variables in your models. Okay? There are limits to what a linear model can do. Now, to be clear, you can also apply this to when you have maybe multiple outputs. It's not just one prediction, maybe multiple predictions. There are all kinds of things you can do. But here we need to talk a bit about what the models start to look like when they get more complicated. Okay? Talk a little bit about computational graphs. Okay? Now, a graph does not mean what it meant in 5th grade, where you have graph paper and you draw lines on it, fun as that is. A graph, in the context of mathematics and engineering at higher levels, looks something like this. Okay? You have little bubbles connected by lines, where these are called, this is called a vertex. And these lines, they're called edges, or an edge. And they connect. Vertices are connected by edges. That's, anyway. And those lines, those edges, they can or may not have a direction. Okay? I'm going to draw a little arrow on this one called a directed edge. People use these in network theory all the time. Like, how do you know that that computer is connected to that computer? And that computer is connected to that computer? And there's all kinds of cool math that you can do when you take a graph that looks like this. You can actually turn it into what we call into a matrix that tells you what's connected to what, and you can do linear algebra on it. It tells you all kinds of cool stuff. Okay? It'll tell you how likely you are to be able to move from one to another. There's a whole it's called graph theory, and it's used in network theory. It's all kinds of neat stuff. That's an undirected edge. That's a directed edge. And this here is an undirected edge. Okay? Meaning there's not a direction to it. But what we're going to be dealing with in this class are going to be graphs with only directed edges. Okay? So only directed edges. We're going to call this a directed graph. You need to know that just so people know what you're talking about. It's like, oh, what kind of connectivity graph do you have? Like what? Meaning that we might have a model that takes in data on one vertex, goes in this direction, hits another vertex, maybe hits another, splits off to two different vertexes, and then back together again, right? Where data might go in, or an input there, and each of these things are functions that act on that data. Okay. This network of connections is the basis of what a neural network is. Okay? Where you have a bunch of vertices, the plural of vertex, okay, that take in data from a whole bunch of other vertices, sorry, and then spit out, and then are transformed through some kind of function and spit out to another vertex. And these things can become very complicated. Okay? It's a computational graph. Consisting of functions which transform data. Okay? We mentioned some of these functions in a previous lecture. We talked about things like a hyperbolic tangent, or tan h. X, that's y equals tan h. The idea is that you have some small value going in, it's some low value going out, and at some point it crosses some threshold, becomes some high value, right? Okay, that's an example of what we call an activation function. That's not super important right now, but that's an example, right? You have and just like our brains, okay, somewhat analogous to how our brains neurons fire. Okay, if a neuron fires too weakly, the neuron next to it might not fire as well. But if it fires strongly enough, it'll activate the neuron next to it, which will also fire. Okay, and how strong that connection is will determine whether or not they fire. So this is a very loose analogy to how neurons work. Okay, but it could be any kind of function. You know, it's up to you, any kind of function you want, right? So we've known for a long time that if you make this network complicated enough with functions that are nonlinear in the right way, you can make this entire computational graph represent anything you want. Anything. There's some minor caveats on it, but that's not relevant for today's lecture. Which sounds awesome. Like, wait, so that's why, in theory, people are very excited in this new AI boom with these giant networks of neurons with billions of parameters connecting all of them. It's like, wow, if you just make it bigger and awesome enough, we can make it think like a person. You know, TBD on that one. To be determined that the current methods will do that. But that's why some people are excited. Like, oh, we can even represent how a person thinks in some way. More complicated than that, but in theory, you have so much power with these connected graphs. Okay? But like any model, if we're going to want to train it, and it's not linear, we're going to have to find a gradient. gradient descent. Here, we just kind of hand wave through a little bit of linear algebra gradient descent for the linear model. It's fine, not that complicated though, right? Here, more complicated. So let's show a simple computational graph. Where you have some input W, not your decision vector W, to be clear, just, I'm running out of letters, friends. Please give me a break, okay? Different W, just an input, okay? And it gives in a directed graph, computational graph, where that W gets passed into some function, okay? And the result of that is X. And the result of that gets passed into another function. Let's just say it's the same function, just for simplicity's sake. And that becomes Y. The output of that becomes the input to another function, F. And the output becomes some final output, Z. So X is literally F of W. And Y is literally, mathematically, F of X. And Z is literally F of Y, not Z. Go away. Okay. Is that making sense so far? This is just a different way to write X is equal to F of W. Y is equal to F of X. Z is equal to F of Y. And if you were to write Z in terms of our input way back here, W, it would be equal to F of F of F of W. Any questions about that? Again, this is a simple computational graph because it's not splitting off and coming back together. That's for not 5 minutes from now. Okay? And as we teased a week ago, that if F is in any way even a minorly complicated function, what happens when we try to use gradient descent to try to change the output of Z based upon W? What does that look like mathematically? Well, if we want to find the partial derivative of Z with respect to W, which is basically the gradient, okay? Well, what is that? Well, I have to take the derivative of the function with all this stuff on the inside, and then you multiply it by the derivative of the inside. There's a rule for that in calculus. Rhymes with the main rule. That's right, the chain rule. Okay? That chain rule causes all kinds of problems because all of a sudden this expression is going to get super long, right? Because this is going to be the derivative of the outside function, we'll call it f prime, and it's still a function of the stuff on the inside, which is f of w. I'm finishing closing off all my parentheses, multiplied by the derivative of the inside via the chain rule, right? Which is going to, so the derivative of the inside here is, so it's derivative of this, so it's going to be f prime, and then the stuff on the inside is still there. So f prime times of f of w. But we're still not done, right? Because the derivative, we took the derivative of this, and there's a chain rule inside of that. We got to take a derivative of the inside of that. And that's the last one, thankfully. We got to multiply it by the derivative of the inside of that. Oh, joy. That adds up real quick, right? Lots of terms. And these computational graphs can get big. So it's really important we want to do gradient descent in a way that doesn't take a massive amount of paper math or the computer doing paper math for us. to efficiently take that derivative. Okay? How can we do that? Well, I'm glad you asked. Okay? Because some of these things actually look kind of familiar if you break it down in a certain way. Right now, so f prime of w, that's just the derivative of a single one of those functions. Maybe not so bad. Okay? In fact, it's really simple if you know your calculus rules. The derivative of a hyperbolic tangent, I think, is secant squared. I forget. Don't quiz me. Quiz you. Okay. This right here, it's just a single derivative of w. But this right here, f of w has a different name here. It is x. It's the result of f of your function going in this way. Right there, that is x. More specifically, f prime of x. Now, f prime of x. Now, this here, y is equal to f of x. That's this right here. F of w, that's two functions of w. That's y, right? That's y. So this whole term, so that there is y. So all of this is f prime of y. So another way to write it is just f prime of y times f prime of x times f prime of w. That's a much more convenient way to write it. But what if we don't know, how do we know what x and y are? Well, here is the cool procedure that people figured out, okay? That let's say we want to evaluate what z is by going through this computational graph, right? We would plug in w, we shove it through our function, we get x. We take that, we shove it through our function, we get y. We take that, we shove it through our function, and we get z. All along the way, we knew what x was. We figured out what x was when we moved forward. Oh, that was x. Store that somewhere in a variable. Boom. Y. Move forward. Y. Store that in a variable. Boom. Z. We got it. So we go forward, and then we say, wait a second. We just got all of that information. We got x, and we got y. Let's go backwards now. Go back, so where we say, okay, we just got y. That's awesome. Let's take f prime of y. Awesome. Right before that, we got x. Take f prime of x, multiply them together. And before that, well, we obviously had w, f prime of w. We went back and computed the derivative really easily without having to do all these complicated functions within functions within functions. We did a forward pass to get the value. Then we did a backward pass to get the gradient. Propagated backwards, and that's why it's called backpropagation. Okay. Okay. Now this is a very, very simple computational graph. There's only one line going in, one line going back. What we want to be able to do, and this will be the last drawing I draw for today, you have some input. And these are all directed graphs, by the way. I'm just drawing them without the arrows. They're all going to the right. Where you can use backpropagation with just a little bit more linear algebra and thoughtfulness to compute the derivative of that in a way that it scales extremely well, that I don't care how many of these vertices you have, or neurons you have, or how many layers we have. We have a way of computing its derivative really easily. That's what backpropagation is great for and what we'll be using it for. Thank you so much. We're at the end of the class. Look forward to seeing your project groups. See you soon. Hey there, what do I got here for you? Oh, thank you so much. Just for me? Thank you.
Like the very beginning, and then it just got better.
Yeah,
so.
that's great. I mean, and it didn't even register, so that could have just been a lag. So it probably got that data's probably on YouTube in the replay. So awesome. Oh, great. Yeah, we did it. Oh, yeah. Hey, thank you very much for your help.